Hi students, we are looking at section 3.4, solving polynomial equations. And some of the vocab that you may remember from graphing polynomial equations is the degree of the polynomial is the highest exponent of a single term. Or if it's in factored form, you need to combine all the x's with addition. And the fundamental theorem of algebra states that a polynomial of degree n has n roots. So remember, if we had a third degree polynomial, we had 3 zeros, 3 x-intercepts. A synonym for that we're using now is roots. So roots, zeros, and x-intercepts are all synonyms. So when we're looking at our examples in 1 through 7, we're going to look at the degree to tell us if we've found all the x-intercepts or roots or not. We'll be including complex solutions, which means imaginary numbers which come from a negative in the radical. So looking at number 1, the degree is 2. So we're looking for 2 x-intercepts. This is a standard trinomial, so we're going to find the x-intercepts by factoring. Because it's a trinomial starts with t, we use a t-chart. I've got the b value of -5, a and c combine to make 4, and so I want -4 times -1 to make multiply to +4, add to -5. Factoring this, I've got 2x squared minus 1x minus 4x plus 2. That should be totally recognizable to you. Then we draw the fence. Factoring out the GCF from the first half, I take out an x, and I'm left with 2x minus 1. And then in the back, I see that it begins with a negative, so I take out a negative, and the number I take out is 2. And that would be positive 2x. That would change to minus 2 divided by 2 is 1. I noticed the hint. I love the hints. They let me know I'm doing it right. So 2x minus 1 and 2x minus 1. My answer is x minus 2 and 2x minus 1 equals 0. So we have factored this, but we have not yet solved it. So in solving, we have one additional step. So I'm erasing my work just to show or regain some of the space. What I'm going to do now is find the values that make the answer 0 after multiplying. And so we remember this first one would just be 2. But this other one is more interesting because it has the 2x. So the work that we do is x minus 2 equals 0, and that's how I got 2. On the other one, we do the same work. 2x minus 1 is equal to 0. I would add 1 to both sides. And then I have 2x is equal to 1, and I divide by 2 to finish solving, and I get x is equal to 1/2. So my two answers are x is equal to 1/2 and 2. So we just have an additional step after factoring. Problem number 2, I can solve again with factoring. This is that special binomial pattern. With a binomial, I do not need the t-chart. I take the square root, and I have x plus 4 times x minus 4 equals 0. And I can just take the opposites here. I've got x is equal to -4 and +4. Really straightforward there. The degree was 2. So let's take a look at a few that are a little bit more interesting by looking at 3 and 4 and 5. So 3 and 4, I both noticed that those ones are third degree, and so is 5. But on number 3, it looks like I can take out a GCF. I see that there's an x in all 3 terms, so I begin by taking out the x. That's going to be x times x squared minus 10x plus 25 is equal to 0. So because I already have one of the factors, x, I know that I've got x is equal to 0 as one of the solutions. So I'm done with that part. Now I go to factor the x squared minus 10x plus 25. So because that's a trinomial, I use my t-chart. I'm looking for -10 and +25. So it's going to be negative 5, and negative 5. And that's going to be x squared minus 5x plus 25. Now that we've split the middle, we draw the fence. And I take out the x. And again, I've got a negative as the lead coefficient on that second half, so I take out a negative 5, giving me positive x and negative 5 again. And I'm left with x minus 5 times x minus 5. So I get the same answer from those. So from that one, I'm going to get 5 both times. X minus 5 equals 0. I add 5. And I get x is equal to 5. I hope you guys remember that from the graphing polynomials unit. But I get it twice. Once, twice. So we say a multiplicity. Oh man, I'm combining my letters. Multiplicity of 2. So technically that counts as 2. So I've got 2, 3 for my degree of 3. Degree of 3, 1, 2, 3. So it's kind of interesting when you get that multiplicity, and then you may remember that that creates a vertex on the x-axis, or that bounce shape. So that one was super fun, but it's definitely in the way, so we got to delete it. Looking at number 4, that type of polynomial has 4 terms. And so the 4 terms does not require the t-chart to begin. Instead, what I'm going to do is start by drawing the fence. And so I want a factor to solve this, which is what I'm doing. And I'm taking out the GCF. I have a negative 3. And we can take out x squared. So I've got negative 3x squared, and then I have x, that'll be plus 8. In the back, I can take out 11. And again, I have x plus 8. So I have negative 3x squared plus 11 is equal to 0. And x plus 8 is equal to 0. So I found my factors and I set them each equal to 0 because I know that's what I'm going to do in all of these sections. Now I'm going to solve for x. So for the first one, I just subtract 8. I've got x is equal to negative 8. That was no big deal. But on the other side, let's take a look. So I know that I have x squared here, and it's not going to factor further because I can't take the square root of 11 or negative 3. So I'm going to use traditional solving techniques. What I'm going to do is subtract 11 to isolate the x. And then I have negative 3x squared is equal to negative 11. Now I'm going to divide by negative 3. Oh, hooray, I have a negative divided by negative. So I've got x squared is equal to the fraction 11 over 3. And how do I get rid of square power? Ooh, I use square root. So I need to actually zoom in on this right here. I've got the square root of 11 over 3. Because I took the square root and I need 2 answers, I know that it's plus or minus. And we're not allowed to leave the answer like this, so I have to remember that this means 11 over 3. I can't take the square root of 3, so that means that I have an irrational denominator right now. So I need to rationalize the denominator, which just means make it into a number. So I'm going to multiply by my magic 1. In this case, it will be the square root of 3 divided by the square root of 3. And then 11 times 3 is 33. 3 times 3 is 9. So I got the plus and minus out front. And then 33, I'm just going to leave that. But the square root of 9, I am going to change to 3. So that means that I've got x is equal to negative 8. And then I've got positive rad 33 over 3 and negative rad 33 over 3. Dang, that was a good one. Very cool. So looking at number 5, we're going to need, I think we're just going to have to zoom in on this. So we have all the space that we need. I don't know why I didn't think of that sooner. So this one is the special pattern. I can't simply subtract 20 or add 27 and take the cube root. Remember, this is that a to the third plus b to the third pattern, which factors to a plus b, and then we have a squared. Then we do the happy face, a times b, but we want the opposite cancellation, so it's minus ab, and then we have b times b. And then this, we will need to use the quadratic formula to to solve that. It always ends up with an imaginary solution. Since the degree here is 3, we're looking for 3 solutions. For these special functions, we end up with 1 real solution and 2 imaginary solutions. So let's take a look at what that looks like. In this case, the cube root of x to the third is x. So I'm going to have x. I match the sign, so minus. Oh, I should have had minus here. And then we have the cube root of 27, which is 3. And then I have x times x, which is x squared. I'll have the opposite sign to get the cancellation, so plus x times 3, which is 3x. And then I do 3 times 3, which is 9. Setting these equal to 0, x minus 3 equals 0 gives me x is equal to 3. But this one is going to need the quadratic formula. I already know it's not factorable, because if it was factorable, I would have factored it further. This wouldn't be the factoring pattern that I memorize. And so I remember that a is equal to 1, b is equal to 3, and c is equal to 9. And I also remember that the quadratic formula says x is equal to, it's the roots, the opposite sign of b, plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. And I happen to know, I've done these a lot, that this there's a special formula or a pattern for all of these in the quadratic formula. It's something like b plus or minus 3 rad 3i rad 3 over 2a. Something really, like, I don't have it memorized. So let's find it out. So I've got negative b, so it's going to be negative 3 plus or minus. Then I always square b squared, so that's going to be 3 squared, 9, minus 4 times 1 times 9, all divided by 2 times a, so just 2. So, oops, sorry. In this case, I multiply 4 times 9 times 1, and I get 36. So I've got 9 minus 36, which is negative 27 inside the radical. So negative 27, that's 9 times negative 1 times 3. The square root of negative 1. Oh my gosh, I forgot about you. It's I. The square root of 9 is 3, and rad 3 stays behind. And so we have simplified the radical part, and I write my answer as x is equal to, let's remember this guy from the beginning, 3, comma, and then we'll have negative 3 plus or minus this 3i rad 3, all divided by 2. And that's the final answer. Ooh, that was wonderful. And so, are there 3 solutions here? Because the degree was 3. Here's 1, and then here's 2, and then here's 3. So yes, there are. Because we would get different values when we added the 3i rad 3 than when we subtracted the 3i rad 3. But I'm not going to make you do that with your calculator or anything, so we're good. All right, let's take a look at number 5. Nope, 6. Oh, thank goodness. Number 6 is very easy.